Hello everyone. Today we will be solving GATE Aerospace 2023 gas dynamics questions. The first question that we have is a 2-mark question, that is question 33. The ratio of the speed of sound in hydrogen to that in nitrogen at temperature 300 Kelvin and pressure 2 bar is. So first of all, let's write down the given data. We've been given that the molecular weight of hydrogen is 2 kg per kilomole. The molecular weight of nitrogen is 28 kg per kilomole. The temperature of the gases is 300 Kelvin and the pressure is 2 bar. What we need to find is speed of sound of hydrogen to that of nitrogen. Now we know that the speed of sound is given by under root of gamma RT. Now we can also see that both hydrogen and nitrogen are diatomic molecules, so we can take gamma or this ratio of specific heats as 1.4 for both. And now R is nothing but the specific gas constant, which can be written as universal gas constant divided by the molecular weight of that particular molecule. So now substituting all these into the formula, we have AH2 by AN2 would be equal to under root of gamma RT divided by gamma RT for hydrogen and then for nitrogen. So now we can readily cancel out gamma from both numerator and denominator along with the temperature. Now we can write R as the ratio of universal gas constant divided by the molecular weight for hydrogen and do the same for nitrogen. Again, here we can cancel out the universal gas constant. So finally this just becomes a ratio of the molecular weights. So molecular weight of nitrogen by molecular weight of hydrogen. So if we substitute the values that have been given to us, this will be 28 by 2, which is nothing but under root 14, which would be equal to 3.74. So 3.74 would be the answer for this question. So the next question is again a 2-mark question, that is question 37. A supersonic aircraft has an air intake ramp that can be rotated about the leading edge O such that the shock from the leading edge meets the cowl lip as shown in the figure. Select all the correct statements as per oblique shock theory when the flight Mach number m is increased. So an image is given in which the theta ramp and beta shock are shown along with the Mach number being greater than 1. So now for this question we will have to consider the theta beta m curve, which is something like this, with x-axis being theta, y-axis being beta. We can draw this for various Mach numbers all the way from Mach number greater than 1 to Mach number about infinity. So as the curves progress, the Mach number keeps on increasing. So if we consider this to be Mach number equal to infinity, and this would be roughly around Mach number equal to 1.1. So here we can see that this theta would approximately be corresponding to around 45 degrees. So yeah, now looking at the options, the first option is it is always possible to find a ramp setting theta ramp such that the shock still meets the cowl lip with beta shock remaining the same. Now what they have told is they keep on increasing Mach number. Here in the first option it is said that beta shock remains the same. So now if we consider a point where beta shock is fixed, let's say this point, here we can draw the corresponding thetas for every Mach number increasing. So we can see that with beta shock remaining the same, there is always a possibility of a finite theta ramp which can be adjusted such that it meets the cowl lip. So option A seems to be correct. So now coming to option B, if theta ramp is held fixed, the shock angle beta shock will increase. Now coming to so let's say we fix theta at this point. Now with Mach number increasing, we have our first Mach number here, which would be beta 1. Second Mach number would be somewhere here, which would be beta 2, this would be beta 3, this would be beta 4. We can see that for a fixed theta, as Mach number increases, beta keeps on decreasing. It doesn't increase. So this option would be wrong. Now the third option is if m exceeds a critical value, it would not be possible to find a ramp setting theta ramp such that the shock will still meet the curve lip, beta shock remaining the same. So we can see this directly from the curve that even at Mach number equal to infinity, there is still a finite theta possible, which is roughly around 45 degrees. So this option again would be wrong. And the final one is shock angle beta shock is less than sine inverse of 1 by m. So we know that the Mach wave, which is given by mu, is equal to sine inverse of 1 by m. Now all the beta or the shock angles with increasing theta would only be greater than mu. So the range for the shock angles would be mu greater than mu less than or equal to beta less than or equal to 90. So this is the range for a shock. So again, this option would be wrong. There can be no angle less than mu for a given shock. So the only option that is correct here would be option A. Now coming to the next question, which is again a 2-marker, that is question 39. A perfect gas stored in a large reservoir exhausts into the atmosphere through a convergent duct. The reservoir pressure is P0 and temperature is T0. The jet emerges from the nozzle at choked conditions with average velocity u, Mach number m, pressure P, temperature T and density ρ. If the reservoir pressure is increased, then, so we have a couple of options that have been given to us. So now they are saying that there is a converging nozzle which is choked. That means the exit Mach number would always be equal to 1 since the nozzle is choked. So now they are also saying that P0 is increased. So let's first write down the isentropic relations, where P0 by P is equal to 1 plus gamma minus 1 by 2 to the power gamma by gamma minus 1. So for m equal to 1, we can write P0 by P as gamma plus 1 by 2 to the power gamma by gamma minus 1. So now if P0 increases, from this relation we can see that P also increases. So the next thing that we would come to is T0 by T. Again for gamma, it would be 1 plus gamma minus 1 by 2, and for Mach number equal to 1, we would get the relation gamma plus 1 by 2. So since T0 is not being changed, just P0 is being changed, there would be no change in T0. So both T0 and T would be the same. So now we can also write T0 in another form, that is T0 is equal to T plus U square by 2Cp. Now since T0 and T remain the same, U square would also have to remain the same. So now the last thing that we would have to check for is density. So now we know that from ideal gas law, P is equal to rho RT. So we know that T remains constant and R remains constant. So if P increases, rho would increase. So now the only option that matches all these conditions is that P0 increases, P increases and rho increases. T0, T and U would remain the same. So the only option that matches all this is option C, where U, M and T remain the same but P and rho increase. So this would be the correct option for this question. Now coming to the next question, which is again a 2-marker, question 44. Consider a one-dimensional inviscid supersonic flow in a diverging duct with heat addition as shown. Which of the following statement is always true or are always true? So now there is a supersonic flow in a diverging duct. So let's consider two cases. One is supersonic flow in a diverging duct and one is supersonic flow with heat addition. Now if we consider supersonic flow with heat addition, that would become Rayleigh flow. So for m greater than 1 with T0 increasing, the Mach number would always decrease, that is M2 would be less than M1. Now here T02 would be greater than T01, and correspondingly P2 would be greater than P1. Now if we're considering supersonic flow in a diverging duct, so let's say area increase. If M1 is greater than 1, then we know that M2 would be greater than M1 because the area has increased. Now we also know that P2 would be less than P1. So considering all these things, let's look at the options. Mach number M2 is greater than M1. So now here we see that in one case Mach number is less than M1 and in the other case Mach number is greater than M1. So it would depend on which effect is more dominating. So we can't really say for sure that M2 would always be greater than 1 or less than 1. So this is not the right option. Next, stagnation pressure P01 is greater than P02. Now if we consider Rayleigh flow, that is flow with heat addition, this would be true. P01 would be greater than P02 because of losses. And if we consider a flow with area increase, if it is isentropic, then P01 would be equal to P02. So we can say that this is one of the right options because there is heat addition. Now the next option is static pressure P2 is greater than P1. Again, similar to the first option, since there is both P2 greater than 1 and P2 less than 1, we can say for sure only if we know which effect is more dominating. So again, this is not something that we can be sure of. Now the last option is stagnation temperature T01 is less than T02. Since this is a heat addition problem, T02 would always be greater than T01 for sure. So the two options that would be right here are options B and D. So these two would be the final answer for this question. So this is the last question in gas dynamics in GATE Aerospace 2023. Thank you for listening.